conclusion of the story. All right. So I meant to mention my collaborators here: Salvatore Bottaro, Marco Costa, Ludovico Vittorio, Xiaoran Sao, and Dario Buttazzo, Paolo Panci, and Diego Redicolo, the last of whom you may know better because they are being around for a longer time. So these are the references mostly I will cover, and some, updates, let's say, of those. And the general outline of my message here is going to be essentially about how you can complement the several approaches we have for dark matter searches, being production in colliders like LHC underground, making dark matter in collisions, dark matter that annihilates in the galaxy and makes cosmic rays nicely joining us with our telescope, and also dark matter interacting in the detectors that we place in underground laboratories. So all of this has to be put together. It's very useful to look at the entire problem in this big picture rather than just in isolation, and you will see how this complementarity play nicely and eventually can lead us to have a conclusion on the existence of this type of dark matter in the coming decades. Okay, introduction probably not needed since you may all be familiar with the story. We know that dark matter is out there. The number of dark matter, say, if you want, the energy density of in the energy budget of the universe is a known quantity. We know. We don't know exactly how the dark matter got to be there. So we need to have the so-called thermal history for dark matter. And a very simple one has to do with a so-called freeze-out mechanism. This is standard textbook matter, so we'll not spend time on it. I guess it's still the most attractive way of getting the relic abundance for dark matter without relying on initial conditions. And this is basically what made the WIMP famous, in my opinion, since it was called the WIMP miracle for a reason. And the reason is that by assuming essentially only weak scale interactions and weak coupling as a mediator between dark matter and the standard model, you can do standard thermodynamical computations and find that relic abundance is the correct size. Now, in the examples that we probably will have to go through in this talk, there is a little bit more of a complication on this specific calculation. It's due to the fact that the dark matter types we will consider are a little bit more than just mere weak interactions, but the basic story is essentially unchanged. So I would like to make this point clear. I'm going to talk about regular freeze-out dark matter, just maybe the computation of the interaction cross-section is actually a little bit different than the usual, let's say, calculation for very well-known things such as X-NOS and WINOS of supersymmetry or similar particles. So the basic story is that you get a relic abundance which scales with the inverse of the annihilation cross-section, all right? And this roughly goes as a mass square for the dark matter, mass of the dark matter square divided by some coupling, which we will take to be the weak coupling, multiplied this coupling by some group theory factor. It depends on what kind of representation of the weak group you are going to use. So in 2021 now, already some time ago, we took the task to the essentially outside. So if you want, we decided to make a big step in certain sense away from the concept that WIMPs are really to be supersymmetric particles. We wanted to not be tied to supersymmetry at all. And we started, actually we continued along by now, I think it's 20 years since people started to do what's called minimal dark matter. We consider generic n-plets for the SU2 weak gauge group of the standard model. And we computed essentially what's the cross-section that you need to achieve to get the thermal relic to be corresponding to the observed number, and especially what mass implies the correct observed relic abundance. And this has been computed for all different values of the representation under SU2. So 3 plets, 5 plets, 7 plets, these are the most natural things to do. because they contain 0 charge and 0 charge states within them, and they are perfect candidates for dark matter. So I will consider other candidates later, but let's focus on these odd representations right now. So 3 plus 5 plus 7 for which you can see that the mass scale is essentially set by the regular annihilation plus it's this line, the dashed line perturbative, plus some other effects that are known as Sommerfeld enhancement, which has to do with long-range force exchanges for this type of interactions, and bound state formation that is also relevant for this kind of dark matter particles. They interact so strongly, okay, that they can form bound states, and they have a mass so heavy that the weak force becomes essentially more long range than what we usually think about weak force. So there are these modifications to the usual calculations that make these three lines, okay, the dots are the final number, and the dashed and the solid are these two less good approximations. So we made this calculation, and we also imposed on this model that would be the standard model plus a single particle that it has some Landau pole, but this Landau pole will have to be at least 1 order of magnitude away from the mass that we computed from the thermal relic. So that at least in a very good approximation, not exact, but a very good approximation, you could say that the thermal calculation for the dark matter relic abundance is not so much different from what you would do in a weak coupling regime. And the interesting message that we got here was that if you start increasing the representation of SU2, at some point the constraint from this Landau pole not appearing too close to the mass of the particle basically requires you to take smaller representations. If the representation is too large, as simple as this, the beta function of SU2 changes too much, and you go into a Landau pole very quickly above the mass of this new state. And the boundary is a blurry boundary, of course. You cannot really know exactly where this thing is happening because it's a matter of definition when you get the Landau pole. But for sure, it seems that a 7-plet of SU2 can still be considered as a weak particle in this respect. Going towards a 9-plet, there are significant doubts. Let's say that this is a weak interactive massing particle, where weak really means that you have, for instance, no Landau poles and no other kind of signs of strong coupling. This is essentially telling you that a 7-plet with a mass that is given in this plot by 50 or so TeVs, it's a valid dark matter candidate, and that it has more or less the same structure than a WIMP. It has some feature arising from bound states and from Sommerfeld enhancement, sure, but it's still relatively under perturbative control. Going to higher masses, you hit the hundreds of TeVs, and not surprisingly, because this was already derived in the 90s as a generic upper bound on the mass for a thermal relic, weakly coupled thermal relic, you hit 100, 200 TeVs possible masses. These are very high masses, and they are not at all impossible in a model of dark matter. They just are very unlikely, I would say, essentially impossible for a weakly coupled dark matter candidate. So with this result, I think, which is essentially parallel to what is this Kim and Kamionkowski bound from, Grist Kamionkowski bound from the 90s, we essentially define that what we want to call a WIMP in our catalog of possible weakly interactive massive particles is something that has at most a 7-plet representation, no larger than that, and a mass that is in the fraction of 100 TeV. Now, this means that there is a finite catalog of particles you want to study if you want to study WIMPs of the simplest kind, the odd SU2 n-plets, so 3-plets, 5-plets, and 7-plets. Now, in this context, I think it's very relevant to mention that there are ongoing programs to develop a new type of particle colliders that will collide muons. And they have the very good property for this problem of dark matter that they can produce the dark matter directly in annihilations. So mu plus mu minus into a pair of these weakly interactive massive particles. And these muon colliders now are, in development, but they have a chance to be, colliding muons in the regime where you can exceed the 10 TeV, probably tens of TeVs. And that means that you have a chance to go close directly with your collider collisions, close to the mass of this dark matter state. Now, this is very unprecedented because the bound at 100 TeVs was known in the 90s already from perturbative unitarity, but the idea that you can make a collider that produces directly these WIMPs by doing direct annihilations of the beams and go so close to this thermal limit, I think is rather a new fact. Note that in this sense, colliding muons is very effective because every single muon collision has the right energy to produce a dark matter pair. This is to be contrasted with proton accelerators, proton-proton machines, where you always have to fish in the proton structure and find essentially quarks of high energy, which make you have smaller cross sections because of the fact that the proton contains the proton is not point-like and contains some quarks which contain gluons, and you are in the end colliding these constituents. So this is giving us a great motivation to study this problem about colliders right now, because there is this ongoing effort to understand the physics potential of muon colliders. And at the same time, as I mentioned before, there are projects for new cosmic ray experiments and bigger high sensitivity, ultra pure detectors to detect directly dark matter. So we want to understand what's the interplay between these two things. Okay,
I'm sorry.
be short. Yes, please.
Can I ask you something about this? Well, the continuous lines here, the red and blue, behind this Landau, behind you see the spin independent only? Is that
No, sorry,
it
that's
means?
SE stands for Sommerfeld enhancement. So you take the perturbative calculation and you add only the Sommerfeld enhancement modification to the cross-section. And then at the end, you also add the bound states. So in correspondence of the 7-plet, let's say you start from 7 TeV with perturbative calculation. It goes around 20 for because of the Sommerfeld enhancement, and it ends up towards 50 for the bound state formation effects. So the dots are the final number.
Yes. And even numbers for this N plet, like 4 or 6, it's not allowed because of why?
If you do it even, then if you have only one particle, this is usually too strongly interacting with the Z boson compared to the spin-dependent measurements. So you have to do something about it. And also for the spin-independent, they also give you too big constraints, too strong constraints. And the trick, I will explain later, but thank you for asking now, is to introduce a couple, like in Xeno, in MSSM, two fermions, one doublet and another doublet with opposite hypercharge, out of which you can form a state whose coupling to the Z boson is cancelled because of the opposite hypercharge thing, and in the end of the day, you are safe. But this requires this adjustment. You have to introduce two particles instead of one. So I usually don't explain it in this slide because it's simple enough with triplets and 5-plets and 7-plets. But yes, you can do 4-plets. I will do 4-plets and doublets as well.
And the other question is why you didn't mention about the electrons and positron collider, for instance? Why it must be muons?
All right. The issue here is that you are trying to make a collider in the mass center of mass range of 30 TeV, let's say. Something that would be a circular collider, let's say, of that size, of that energy, sorry, for an electron-positron collider implies that in the moment you bend the particles for the circulation around the ring, the electrons radiate a lot of energy into synchrotron radiation.
More
and in
than
that sense, muons are very advantageous because being 100 times heavier, and this effect scales with the fourth power of the mass, muons are very much well behaved in this sense. They give you a lot less radiation, so you can really circulate beams of these energies. That's the same effect that you have when you do protons instead of electrons. You do not have so much synchrotron radiation that eventually you have to compensate for. And muons have this advantage of being not radiating so much, and at the same time they are point-like particles, so every muon-muon collision is the same as a plus and minus. It hits the center of mass energy precisely without energy loss.
Okay, thank you.
Yeah, if there are other questions, I'm happy to go faster on the rest later and discuss here. Otherwise, I'll go ahead. Okay, so this is a little bit more technical. As I mentioned, there are these bound state effects that are part of the Rayleigh calculation. I don't want to spend much time on it, but it's part of the Rayleigh abundance calculation. You have to include these new interactions. They have to do with the fact that when the dark matter come close to another dark matter, they can form a bound state. And also the fact that when they come close, they can start to feel the weak interactions and this form bound states through that and Sommerfeld enhancement. There is some technical aspect that has been figured out already some years ago, how to make this calculation simpler. The references are on top. What's the important thing is that at the end, you can almost rephrase it as if the weak coupling was different from the value that it normally has with an effective coupling. So the understanding is essentially the same as a WIMP, regular WIMPs. It's just that for each mass, you have to recompute some factors which make the calculation a little less predictable than what you do with regular WIMPs. But in the end, you get very definite answers in this case. Those effects especially can become a little bit, they can take a little bit of computation, and sometimes there are uncertainties associated to that. So that's why I go again here in this slide. You see that for big n-plets, if you do not care about the Landau-Paul issue, we started to put error bars. So then the thermal Rayleigh calculation, if you take into account how well you can compute Sommerfeld enhancement and bound state formation, you will have to admit that with perturbative techniques, you start to have an error bar in this calculation, and we decided to show it in full just to make clear to the readers that by having computed the accuracy that we were computing back then, we knew basically better than the order of magnitude of the dark matter mass, probably the second digit, it's known. And even the third digit sometimes. The problem is that if you really wanted to entertain a large n-plet, then you should really be worried because you cannot even compute this value for the Rayleigh dark matter mass. All right, so as you said already, this is for hypercharged zero odd n-plets. There are other possibilities I will cover later, but that's the general message I wanted to give. We can say compute these masses reliably and show error bars for them, so we know exactly what is the target that one should reach for these very simple models of dark matter. I would like to stress here that G here is a fixed number, is the weak coupling. Cn is a coupling Casimir effect, sorry, Casimir factor that is also fixed once you fix n, and the mass, therefore, it's a sharp prediction. There are no moving parts in these models. They are extremely predictive. Now, what you want to do to this model is, of course, to go in the lab and test it. And the labs sometimes can be a cosmic ray observatory, so it's not exactly a lab, but you can do lab experiments like a xenon experiment to search for dark matter directly coming from the, say, cosmology, from cosmogenic dark matter, or you can try to produce the dark matter so that you can control more and more its properties, let's say at the LHC or in other colliders. Now, my message here is that these three things needs to be done, all of the three at the same time, and they have to make progress, on the same timeline, because we will have several interactions between these experimental programs. I will give you details in a moment. Now, for cosmic rays, essentially the game is that you point your telescope at some galaxy or to the center of our galaxy and try to find annihilations into some specific signal. There is, let's say, a classic way of doing this, that is the annihilation of dark matter into photons. Photons are very clean, in a sense, for observation, for instance, by the CTA experiment that is running in the 2030s at full regime. And that's sensitive to photons up to 300 TeVs. So it's perfect to go after this kind of very heavy WIMPs, okay? Here, the results that are expected are very interesting because pointing this observatory to the sources, you can be sensitive to cross-sections that are compatible with what you expect from dark matter annihilation. There is only a caveat in these experiments that the cross-section bounds that they give you are, of course, objective and they are what they are. The interpretation in terms of a dark matter search requires you to know the cross-section for the dark matter to annihilate into a pair of photons. And this has a significantly complicated structure that I'm showing here in these red and blue plots, red and blue Caspi lines that have to do with essentially how well the dark matter annihilates into photons. Sometimes there is a very big enhancement in this annihilation that is due again to Sommerfeld enhancement effects. Sometimes the enhancement is not as big. It has to do with meeting or not certain resonance conditions. So under some certain lucky conditions, you get very big signals. And so the spikes that you see in the cross-section prediction are larger than what experiments are going to be sensitive to, like over here, over here. In other cases, the enhancement is not as big, and you may even have what looks like a dip, like over here. So the precise value of the dark matter that you will be searching for affects the interpretation. And therefore, there is a bit of a lottery. You can be lucky and you observe dark matter in these experiments. You can be a little bit unlucky and you do not observe it. So it is very interesting to run these experiments because they can give you a positive signal of observing something that looks like dark matter annihilating to two photons. But you cannot be sure if you did not observe, if you can exclude dark matter, because you can be, ending in one of these dips where the prediction is unfortunately lower than the experiment sensitivity. There is also another aspect that has to do with the fact that annihilation in the galaxies depends on the distribution of the dark matter in the galaxy. And here I'm not a terribly expert, so I'll just show you results from other people. Depending on how much Caspi, the dark matter distribution, is around the center of the galaxy, you may or may not get big enough signals. So these colored lines for Winos and Xenos that are my triplet and the pair of doublet we were discussing before. These authors have shown how by changing the size of the dark matter cusp region, the core region in the dark matter distribution in the galaxy, you can go from a very large cross-section, a very big bound over here in purple to the very stringent bound on the red, depending on the shape of this dark matter profile. And the relevant number for this candidate, for instance, is this blue band for thermal Xeno. So depending if this value of the core region is bigger or smaller than 2 kiloparsec, you can put a relevant bound or not. This is something not under our control, I would say.
Sorry,
so here please.
Sorry, can I interrupt you? So the red or the color lines here are upper bounds or what?
Yeah, you are excluding everything above the line. That is a cross-section larger than these numbers. And the color represent how Caspi is the shape of the the profile of dark matter. So here you can find different profiles, EINASTO, NFWs, and other profiles that are used in the literature. I wanted just to show that given what you assume for these dark matter profiles, you can get significantly different densities in the central region, and these affect the flux for the annihilation into photons. And these plots.
But I mean, sorry,
yes.
but yeah, I understand that. Okay, so, but okay, it depends on the density profile. I understand that, but the upper bounds were made by some indirect detection experiment.
Yeah, this is a forecast for, I think, it's still in the...
forecast.
Yeah, it's a forecast. So let's say the strength of these bounds, again, interpreted as cross-section from annihilation of dark matter, varies according to what size of, what is the size of the core region where you expect to have a lot of dark matter colliding for you.
Okay.
And that you have to confront with this
with
again,
your
Caspi lines that are coming.
Yeah.
In this case, they are using two different models for Exynos, where the splitting has to do. The way the two doublets are degenerate is changed. In the left plot, instead, for the WINO, there is only one prediction, because in that case there is no need to change this. There is only one particle, so the prediction is a bit sharper.
Okay, but maybe because I haven't heard about this forecast experiment. They measure photons, gamma rays, I guess.
Yes, exactly.
Okay, thank you.
Okay, you're welcome. So my point again is that there is a bit of luck that is involved into finding dark matter through indirect detection, and we don't have these factors under control. So we need the other perspectives. Another result that gives you the same message, I probably have to speed up a little bit now, is about these so-called Milky Way analogs, in which numerical simulations of galaxy formation essentially give you pairs of galaxies like Milky Way and Andromeda, and in those galaxies that you form in the computer, if you want, you can check the profile again, and you see that there are significant deviation given the type of, which replica of the dark matter of the Milky Way Andromeda pair you pick. For instance, in this paper, they computed how strong would be, if you want, the test statistics. So how big is the evidence for dark matter, for Exynos, especially in this case, under the assumption that you use a pair of of galaxies that go under the name of Romeo and Juliet, or what's that, Thelma and Louise, or other pairs that you find listed over here. And you see, some galaxies, they have a dark matter distribution that give you more than 10 sigmas evidence, okay, at CTA experiment. Other, they don't. They have, like this one. This is probably Romulus. So that's the name of the galaxy that they gave. It gives you a barely 1 sigma evidence. So there is a distribution on, of results that again makes us not sure that by not observing this Exynos, for instance, you would be able to say that the Exynos do not exist, because you might just live in an unlucky galaxy where the dark matter is distributed in a non-friendly way. Let's say you live in Romulus, or you live in this other M1-M, or whatever, even this, other galaxies like this. Louise gives you a few sigma only, so you may be lucky or not. So it's a kind of uncertainty that you have to understand what to do with. Now, these results are expected in the 2030s, so we need to be tuned on this news coming from the dark matter world. In the same time scale, there will be progress also on the so-called big tank experiments, xenon tank experiments, in which you try to see dark matter annihilating on a nucleus. And these annihilations can be computed, again, in perturbation theory, and you can find the predictions for the amount of spin-independent, especially dark matter cross-section on the nucleus that we put in this plot over here. Again, here I'm showing first odd n-plets, so 3-plet, 5-plet, 7-plet, and so on, for the mass at which we predicted them to be in our work. And you see that these particles are very much, suppressed cross-section that have not been observable so far. So xenon 1 ton, for instance, they are not able to see these particles. But the future upgrades eventually will be sensitive to them. So you can go and look at upgrades like LZ and eventually Darwin, and they will bring these bounds lower and lower. At some point, they should expect to be sensitive to all of these odd particles, odd n multiplets. That's a very interesting message. These experiments, unless there are new uncertainties that have not been understood, they should be sensitive to these particles, and they will give us a positive signal. Or if they don't, it means that these particles are probably safely excluded from the list of candidates for WIMPs. There is an important aspect of this discovery when it will happen that has to do with telling us that there is an excess, yes, but what mass the dark matter is causing, what's the mass of the dark matter that causes this excess. This will be a task at which these experiments will not be very good, because essentially they don't know the difference between a 100 GeV dark matter mass and a 1 TeV dark matter mass or a 10 TeV dark matter mass, because in the moment that the dark matter mass is larger than the xenon nucleus mass, essentially this becomes an irrelevant parameter for the experiment, for the detection. So they don't really know. And in this volume of 2022, in fact, the xenon experiment published this nice plot where they show us what would be looking like to have a 20 GeV dark matter injected in their detector. That's the red island on the left. And what instead would be the shape of their likelihood for 100 GeV dark matter. And they would basically know that there is a signal, but they wouldn't know exactly what cross-section to assign to that. Because for different masses, they would get different, let's say, so different masses, they would get essentially compatibility with different level of cross-section in their detector. So they will not know what's the mass of what they discover if they discover these particles. Again, very interesting, but probably we need to know more. Once you got this excess, you want to know what's causing it. All right, so so there are these scenarios where essentially you can have detection at let's say indirect detection experiment or in a direct detection experiment, which will still need to be interpreted for to understand better what has been discovered. Plus, there are scenarios in which there is no sensitivity in xenos, for instance, from indirect detection, and there is no sensitivity from direct detection as well. The reason has to do with some special features of these xenos. I'm now finding the slide to show you that, but essentially there is a chance where, yeah, that's the best slide, where you can observe here these points on the bottom left of the plot where doublets have been computed their cross-section on the direct cross-section for xenon, and they are below what is called the neutrino floor. All right, so everything that is under a certain level of cross-section in these experiments is very hard to measure, because there starts to be background from neutrino production from the sun and the atmosphere. So eventually these experiments are becoming so sensitive that they see these neutrino sources, and these neutrino events are very hard to distinguish from the dark matter signal. And in this case, this makes us pessimistic on the fact that a direct detection experiment can observe convincingly a doublet dark matter, scalar or fermion, or even some kind of the 5-plet with hypercharge, if one want to be more general and consider even more dark matter candidates. Still, I would like to highlight that there are lots of dark matter candidates for which these experiments are expected to see signals above the neutrino floor, and they are gonna be, I would say, smoking guns for dark matter. So Yeah, you can make this plot more refined. This is what has been done in 2024 very recently by a subset of our collaboration, considering again odd and even endplets with in full glory. And you see that again there are doublets that are not doing well. They are under the level of cross-section that Xenon can observe. Yeah, this one I would like to skip. It's about making further adjustment in this mass spectrum by adding higher dimensional operators. But if you want to know, I can tell you later. The message isn't changed. The perimeter space is those squares. In the yellow part, you still have neutrino fog, so you don't observe it. Now, this is where I think particle colliders become extremely relevant. There are these two scenarios in which you might have a hint for dark matter in either indirect or direct detection. And then you want to understand better what you discovered, and then you need a collider. Or you may not find any signal from dark matter at these xenon-like experiments and indirect detection. In that case, there are a very few number of possible WIMPs that are left, alive, not excluded. In that case, you need to be, of course, hoping for the best, that maybe some WIMPs of those types are there in nature, but you need a new experiment to probe that because there is no way you're going to probe it with xenon, and maybe only if you're lucky with indirect detection. So this is a well-known subject. There are several ways to attack the problem from collider perspective. It's mostly controlled by how large is the splitting within those large weak multiplets. So let's say if you have a triplet, you have three states, and the mass splitting between these three states is what determines how these states appear in your collider experiment. So depending on what you do for this dark matter mass splitting, you get different type of collider signatures. Here I'm making a list. A very nice one that is pretty generic in these models is this short disappearing tracks. I will give some details in a moment, which essentially has to do with the production of one of those endplets, but especially production of the charged particles. So if you have a triplet that contains a charge 1 and charge -1 and charge 0, the charge plus and -1 will leave potentially some signals in your experiment, whereas the charge 0 is the dark matter and it gives no signals. When you produce the charge 1 or -1, they eventually decay into the charge 0, that is the lightest of the endplet. And when they do that, essentially they leave a short track in your detector. And this short track can be detected, can be seen, and it's very distinctive because there are only limited number of standard model backgrounds to that kind of signal. So people have started this very extensively since a very long time by now. Probably, I would say, at least 20 years of study have gone this in the LHC and now in future collider experiments. And the results are summarized in this over here for Xeno and Winos. And you see that there is a very good chance to observe these objects. For instance, if you build an FCCHH machine, a PP machine at 100 TeV, you can observe and even discover, actually, 5 sigma discovery, an Xeno of that kind. PP machine in this case is a 100 TeV machine. And please note that if you instead make a muon collider at 10 TeV, so 1/10 of the center of mass energy, you will be able to have essentially the same discovery reach and only slightly worse sensitivity reach. So it's very much equivalent to run a 10 TeV muon collider than a 100 TeV proton machine. Now, for reasons that have to do with how these machines are constructed, an E plus C minus can be or still be built at some energies, but it has to be linear for what we discussed before. Circular 3 TeV would radiate a lot. And in this case as well, it's possible to observe this type of thermal Xeno dark matter. So there are these proposals out there for future colliders that are very promising to attack this very difficult otherwise thermal Xeno dark matter model. As I said, difficult for direct detection and maybe yes, maybe not for indirect detection. So these machines are ideal instead to attack this problem. And also now there is a recent result from this year where also for muon collider 3 TeV, it has been essentially they found better ways to attack this problem, and even though the result is still a little bit worse than what can be done at the plus minus, still now there is a new technique to attack this signal that gives potential for this Higgs Xeno also at the 3TeV machine, Muon Collider 3TeV machine. All right, so basically, there is a range of options in future colliders which can be sensitive to this scenario of dark matter. I have to say that there is also a range of timelines in this aspect. For instance, another machine is supposed to run in the 2060s. So this is a timeline where PP machine can appear, and it's quite far away compared to where dark matter timeline will populate us with new information. So this is an unfortunate delay that one has to, let's say, suffer in this case. There are other ways to look at these particles. They have to do with observing the production of the dark matter particles in association with vector bosons, or other more elaborated, let's say, searches that you can do in colliders. But I want to be quick on this and just show that if the dark matter in one of these colliders, shows any of the other, signals that I'm constructing here, and especially if it is very degenerate, you can do this kind of mono X searches, which are very powerful to search for this dark matter. So in these mono X scenarios for searches, you have several results. Each color here represents a different type of muon collider, for instance, from 3TeV to 100 in principle. And you see that it's sensitive at every energy that you pick, you can be sensitive to more and more dark matter candidates in this way. In general, you have best results by doing monophoton and mono W. With comparable results and some experimental aspects that are a bit different. Now I don't want to enter in the details, but there is a nice complementarity that you will observe this signal not in one type of observable, but in at least two that will make this observation very robust. Yeah. So in general, you can concentrate if you want on the small representations like Xenos and Winos, and in this case, you can really have good results, very good results with a 10TeV machine on top of what we discussed already. If you do this tracklet result, which gives you sensitivity already at the 3TeV machine. Now, a muon collider should be placed on a timeline. This is a matter that is being discussed in these days, but it is mostly seen as a type of collider that you would run independently, let's say, of any Higgs factory like an plus minus circular machine. And so it has a chance to run in the 2040s, so maybe in the late 2040s, but in the 2040s. And this is a timeline where probably you interact better with the results from the dark matter experiments. Let me skip on this. And also here, I wanted to say, in principle, there is you can consider large energies like 30TeV muon collider, and so eventually you will be sensitive to some of the candidates I mentioned before, for instance, the 5-plets. But you will always have some particles that are too far to be observed directly. No track signal, no mono X signal. They are too heavy to be produced. In that case, you can still have another approach, this precision test. So in this case, what you do is to imagine that there is a new particle that changes the weak boson propagators, and you compute essentially radiative correction to fermion scattering into standard model particles. By including these new states in these virtual effects. And at the end of the day, you can compute, for instance, angular distributions for the standard model final state you want, or the total rate that you want to compute. And the result essentially is telling you in a moment is that there is a new way, even say a further way to attack the existence of dark matter thanks to this, say, indirect sensitivity. Indirect because you are searching for the chi, the chi particle without producing it. You just see its loop effects. Okay, so summarizing here, I want to be quick. Yeah, this is a typical result where essentially you can take a given center of mass energy and a given luminosity, and you can find what luminosity is necessary to run your machine at that energy to make a discovery or to make an exclusion. And the result here is a bit complex to read. I will give you in a moment. Is that essentially you can probe triplets, for instance, with a 3 TeV machine. You can probe doublets and fourplets with a 10 TeV machine. And if you can afford the bigger machines like a 30 TeV or something like a 50 TeV machine, you can probe 5-plet of all kinds, but also 7-plets. In principle, you would probe a 9-plet if you were interested to that. So there is if you wish, a stage after stage of machine improvements that will give you more and more dark matter particles under your microscope. If you want to stop at the 5-plet level, because that's probably where, for sure, perturbation theory makes sense for a WIMP, you can do that. In that case, a machine in the range of 10 to 20 TeV is perfect. If you want to reach 7-plet, you need to run maybe a 30, 40 TeV machine. But the message is pretty clear. Once you improve on your energy on your muon collider, you will be sensitive to new dark matter candidates. And overall, essentially what is happening is that you can take the old list from 7-plet down to doublets, including all the triplets and 5-plets and 4-plets, which I haven't put in the list, but they are there. And you can make exclusions at each stage of one of these muon collider machines. Eventually, if you will run a PP collider, you will be excluding also some of them, but not all of them, because the effects at the PP machine are too small. And in fact, here is a summary plot for those who like electroweak precision test. I don't have time now to explain what it is, but one of those propagators modifications can be cast as a so-called W parameter. The W parameter at a given center of mass energy of the muon collider gets a bound that is better and better as you increase the energy. And for each of these new dark matter candidates, you have a prediction how big is this W parameter. And eventually, as you see, if you take, for instance, a triplet, it cannot be probed by the W parameter at the muon collider, let's say 5 TeV, but 5-plet will be probed doing 20 TeV, for instance, muon collider. So there is a very systematic way of probing all the candidates. And eventually you will exclude larger representations like 4-plets, 5-plets, and 7-plets thanks to this method. So that's why I say that essentially all the particles in the list are excluded by this method. So this is a big novelty. I don't know if you realize, because I've taken a theoretical idea that is the exclusion. Sorry, that is the fact that the dark matter is a thermal relic, which is it's since the 70s in the phenomenology playground. So it's been around for 50 years or so. And I've made the biggest catalog you can imagine, I suppose, for a WIMP. And now I'm telling you that there is a systematic way to probe it up to the very end of the catalog with just, quote unquote, bigger colliders maybe, and these other approaches from dark matter that I mentioned before, dark matter searches from cosmic rays and in direct detection on xenon nuclei, for instance. So that's a pretty remarkable fact that brings me to my conclusion. We have this big idea of dark matter being a thermal relic. Today it's moderately not so in fashion, I would say, because people after so long got tired in a way or interested in other kind of dark matter candidates. The results that we have so far are partial. There are only certain candidates have been tested and not at all the entire set of possibilities for WIMP dark matter. In part, the pessimism around WIMP in these days comes from the fact that WIMP has been traditionally associated to supersymmetry, and now searches for supersymmetry are also not returning any positive result. So people is a bit pessimistic. But if you decouple these two things, you don't care about supersymmetry, you just care about having thermal relic dark matter. WIMPs are very well alive. And as I shown, there is a big catalog of potential candidates we need to search for. Okay. And some experiments will be really, hopefully in the next 10 years or so, give us some direct evidence for it, or indirect, but still a positive evidence, like peaks and gamma rays. If that happens, we definitely have a scenario in which we need to go further, investigating further what's the origin of the signal, and the dark matter search at colliders becomes a priority. If these experiments are not giving us a positive evidence for dark matter, I think I discussed the fact that there are very well motivated examples of very simple models that escape the sensitivity of these experiments because of accidental facts. Either they have a too small cross-section on xenon nuclei, or the amount of signal that you would get in gamma rays and cosmic rays, it's depending on other, environmental astrophysical quantities, such as the dark matter profile, that just might be, bad luck that we cannot find dark matter in that way. At that stage, again, I think if you want to go and finish the job and explore till the very end of the book, till the very end of the catalog, these dark matter candidates, you need to again run colliders. So this is bringing in, I would say, a big motivation to go for a muon collider in the next future, because with that kind of machine, together with experiments on dark matter that are coming in the, say, 10 years or so before the muon collider, you will have a chance to test the entire catalog of WIMP dark matter up to the perturbative unitarity limit that I mentioned in the fraction of 100 TeV mass range. And yeah, that's where I think also time consideration are very important. Here you see what is being laid in 2020 in the process of European Strategy for Particle Physics as a timeline for possible developments for our field. And you see there is the high luminosity until the beginning of the 2040s, essentially, but high luminosity LHC, followed by other projects. One project is this FCC-EE and followed by FCC-HH, which is gonna start in the mid-2060s, which in my opinion is a bit late compared to the fact that dark matter news from the Xenon experiment or CTA are coming during the 2030s. So there is going to be a 30-year gap in case you want to wait for the FCC-HH. On the other hand, there is a chance that we can do something around the mid-2040s with a muon collider proposal. And that should be taken very seriously if we want to interact very, effectively with the dark matter searches and the dark matter community. So in this context, I would like to simplify that timeline I proposed before and to highlight that there is a chance in 2045, late 40s, let's say, to have a muon collider. We should study that very much. And I would say also encourage our, accelerator physics colleagues to do studies for this, because that's potentially the best experiment to test the idea of WIMP as a dark matter. And to me, this is a lot better than having a 30-year gap before going to FCC-HH, which will have some potential, of course, but as I said, not the ideal timeline. So my conclusion is essentially that with these three approaches, and here I'm playing the metaphor of a chessboard game, we can frame the dark matter just in one corner where it cannot escape anymore because there is an experiment ready to detect it in any direction it can move. And you see that it is very important to put together these three approaches. Thank you very much. That's all I wanted to say. Thank you for your attention.
Thank you so much, Roberto, for the very nice and very comprehensive talk. Thanks a lot. And the question from the audience?
Yes.
Okay. Go.
Sorry.
Well, thank you. My question is, maybe I didn't understand very well the one of the slides or the results that you showed regarding this upper bounds coming from indirect detection when where you show this density profile of the galactic center based on that. So, but those upper bounds are prospects, they are not they were not constructed based on real data, right?
Let's say if you
No,
know,
it was before that, sorry.
Yeah, it's the same type of problem, if you wish. These indirect detection experiments, like CTA, the experiment I think is being built right now. They have a very small fraction of it commissioned, probably not. Probably, I don't know if it's even taking data. So you need to understand what kind of data you will get. Assume something about the resolution, let's say, for this measure, the gamma rays that they can detect. And based on the experiment, you will find the kind of bound that it's going to put. Then, to interpret it as a dark matter signal, you have to assume what kind of signal you're getting and from which regions it's going to come. Okay, so there is a directionality aspect on top of it. Now, the resolution, you can see here, can play a significant role because this SVWGO is another experiment that is in the South Pole, but biggest difference is that it has a worse resolution than CTA. So you see why with bad resolution, the experiments, worse resolution will give you smaller sensitivities. So this number of sigmas, if you wish, if you do you pick the blue experiment, is always worse, all right? So you have to fold in that kind of aspect, resolution. And compared to this one, there is also an aspect related to which source is gonna be brighter. If the profile of the dark matter is more cuspy, so you have more concentration at the core, you will get a brighter spot in your experiment, and then you say your sensitivity is better in that case.
Okay.
That's my understanding, of how these experiments operate. So having a good energy resolution and some directionality, of course, gives you let's say a rather a good result if you have a cuspy result and a good detector resolution, or you could get a worse result if you get the core that is more widespread, so there is less bright spot in your signal, and the resolution is worse, so the energy that you see is not well measured. And you see it can make a big difference. The orange bars are a lot better than the blue bars comparing these two experiments over here.
Okay, and for instance, according to Hess experiment, for instance, it has been possible to constrain this type of scenarios?
Yes. So S is making a similar measurement, but at smaller energies. Yeah, but it's still a very constraining experiment. So I think, according to some authors, the thermal WINO, it's actually pretty much excluded by Hess. Okay? Thanks to the fact that you see the WINO has a bigger cross section. Its thermal value can be in the range of 25 or so, minus 25, sorry. Whereas the Xeno, it has a range of cross section at the level of 10 to minus 28. So Xeno in this game is always going to be some kind of a nightmare scenario. Unfortunately, WINOs are a bit easier. And according to some, let's say, there is even the claims around that the WINO triplet in my languages should be triplet of hypercharge 0. It's already excluded, in fact, by ES. But I would say that in any case, future data from from CTA will help to make even more strong, say, case for WINO being excluded if it's excluded.
Sure. My last question is, you mentioned something about inelastic dark matter. So in this type of scenarios, in principle, you can have that type of behavior according to the mass splitting that you have here?
Yes, so the idea is that once you scatter into nuclei, if there is, let's say, an interaction of this type, you have to excite essentially the charged component of the dark matter multiplet. And if this chi plus is too heavy, and heavy here has to do with the momentum exchange in the scattering with the nucleon, which is very low, you effectively get a suppression in the rate in your rate for interaction. So that's the idea of inelastic dark matter. Now, who generates this mass splitting? It becomes a model building question, all right? The splitting between the two doublets has to be arranged to be large enough that this mechanism works. It is doable. And in fact, what I wanted to highlight is that we studied even how you could do that by adding higher order operators like chi-chi interaction with Higgses. It's generically a possibility to split them quite enough, I would say. Where is the plot? Yeah. So in general, you can populate a plane, let's say for a doublet, where the splitting between the neutral states and the splitting between the charged and the lightest neutral can range in very big numbers. In MeVs, you can go from 10 MeVs to 10 GeVs, essentially. They can be obtained by adding operators like this chi-chi x square. They can be, okay, some of them are a bit extreme solutions in the sense that this operator needs to be suppressed by a very low scale in order to give you a big effect. But let's say, all you need is to survive something like from Darwin or go in the neutrino fog. You can basically go and move a lot around this plane just by exploiting this inelastic-like behavior, if you wish.
So all that region in orange, it is supposed to be excluded by Darwin.
No, that's the inaccessible region. It's the neutrino floor.
Inaccessible.
The green, you see green, the outer green, and then another sliver where you have another experiment, and then eventually you have the future experiment, LZ and Darwin. So everything that is larger than that, it's not, it's going to be tested. But at some point, the experiment hit again this neutrino floor, and you don't have anything. Well, I don't have much to say except that it's difficult to probe, probably not possible at all to probe.
Okay, thank you very much for your nice presentation.
Thank you for the questions.
I have I have a remark. First, thank you for a very, very nice talk. But I have seen that all the simulations, all the cases studied are for fermions and scalars. What about vectors?
Vectors is a complicated story because this is what we studied is what you would call matter fields, so fermions and scalars. If you go into gauge, sorry, to spin one, it looks like you are extending the gauge structure of the standard model, and then a lot more possibilities open up, I think. First of all, this vector will have a coupling that it's probably 3 parameter of the model. It's probably connected to other matter, because if it's a gauge boson, let's say it's coupled to the our standard model fermions, is going to be coupled probably to other fermions, one of which could be the dark matter. This is another type of model. So it's generically possible to have a thermal relic from this kind of models, but they have more parameters, because the coupling of the new vector to our fields, to the standard model fields, and to the dark matter are 3 parameters on top of the mass of the vector and the dark matter mass in case this object is not the dark matter itself. So generally, these are bigger parameter space models. And instead here, what we wanted to do is to take, let's say, essentially this is a 0 parameter model, at least until you start adding these higher dimensional operators. And so we wanted to study a very specific, so a very predictive scenario. In the other case, you can have a freeze-out mechanism with vectors, for instance. But again, there is a whole range of possibilities. Now, generically, if you do have an exchange like here, I'm doing chi-chi exchange into a nucleon. If you have an exchange instead of with the Higgs, with this spin one that you are considering, it's very likely that you have a too big rate and you are excluded already from the xenon-like experiments. If you reproduce the thermal, the relic abundance by freeze out. So, for instance, for a purely vectorial coupling, which is a possibility, you can also have a little bit of axial coupling. Generically, you encounter that kind of problem. So, if the cross section is such that you get the thermal relic, so yeah. If this sigma annihilation is the right side, so that gamma omega is correct, in that case, you typically get annihilations that are the cross-section into xenon is too large. This is definitely the case if this is a vector coupling. You can try to escape a little bit adding axial coupling, but even there, I'm not exactly sure how much space there is left. But to say that this is definitely a possibility, you're totally right. Then there is this issue that you have more parameters, so you become less predictive. I hope I answered to your question.
Yeah, I asked because it is possible to consider matter fields with spin one. I mean, spin one matter field, and in particular, the triplet is very minimal. It's very minimal. The quintuplet is much difficult. You need to introduce some non-minimal interaction. And but the problem, for instance, with unitarity, which are usually the problem with the spin one matter fields, can be put under control. I think the minimal vector dark matter is quite viable, principally for the triplets. I can say that because I compute that.
I got the feeling. Nothing against that kind of models. Absolutely. I think still there is a little more freedom in how to build them. Also, the issue you mentioned, unitarity, you have to give a mass to these vectors. So you need a bigger story, to make this vector matter to be consistent. So you have to be very, say, compared to this, it's a non-minimal scenario, I think. So we wanted to concentrate on something very predictive in which you could see the complementarity between these 3 approaches. But definitely, I'm sure if one wants to engage into a little of model building, you can construct a model for this vector object. And I suppose you will have the same degree of interplay between different experiments.
The vector, the case of triplet vector only has 3 parameters: the mass of the vector and the coupling with the Higgs.
So the mass of this vector is coming from the Higgs mechanism?
No. It's put by hand. I mean, you consider a vector which transformed homogeneously in the adjoint representation of SU2 as a filter. And it's not a Gauge boson. It's not a Gauge boson.
Yes.
So the mass is a free parameter.
And I mean, somebody has to generate the mass of this object, right? It's not. I mean.
No. The gauge symmetry allows a bar mass pair for the vector. Of course, this is an effective theory. You can, but you can put a mass term in the Lagrangian for the vector dark matter without violating the gauge symmetry, because this is not a gauge boson; this is a matter vector boson. And
in the triplet representation,
in the triplet representation, yes.
Okay. All right. No, that's definitely an interesting option. And you thermalize it by coupling to Higgs. Did I understand correctly, or you have...
Yes.
Okay.
Yes.
Then I guess we can discuss more in a separate context.
It's
another interesting example of rather minimal model that can be placed somewhere here in this plane.
Yeah.
Can I comment something about this? Well, it's a question more than a comment, but considering that, well, in my understanding, there are no bound states made of vectors. I don't know if in this type of scenarios with multiplets, vector multiplets, you can have this type of effects, like, because the Sommerfeld effect, it's possible, Alfonso, right? You have calculated those effects, but in terms of bound states, is that in principle possible with vectors? Because bound states of fermions, it's something that we already know very well from QCD. And
I think it's possible. Huh?
In principle, there's nothing that forbids that.
Yeah.
But in nature, have we observed something similar, like in QCD, for instance?
That's a different question. But let me also say that bound states are not very important for triplets. You see, Sommerfeld enhancement in the triplet is already giving you a difference between the perturbative and perturbative plus Sommerfeld. But the addition of bound state doesn't change anything compared to Sommerfeld calculation.
Okay.
So for triplets, yes, you are right to ask the question. It's a legit question. Do you want to consider bound states or not? Are they allowed or not? Are they breaking any conserved symmetry or something? But even if you put them, they will not change the relic, at least to my knowledge.
Okay. Thank you. Thank you for your presentation.
Thank you, guys.
Roberto, I had a quick question. In one of your plots, when you show this peak and did for the thermal average cross section as a function of the mass for the 7-plate representation, how this you would expect to change, for example, instead of having the 7-plate representation, you will have the quintuplet, for example. This thermal cross section, I suppose that will have lower
values. They are generally smoother.
Smoother. And the distance between the peaks?
Okay, this is a detailed question. I don't know if I can give you an answer, because it depends a lot on you know, meeting or not meeting these resonance conditions. And I think there is an understanding of this as a a function which has more zeros as you increase n. So I would expect that you have a bigger number of dips and peaks oscillations as you get larger and larger n. But yeah, that's the only qualitative thing I can say without looking further in the calculation. But in general, let's say the bigger the representation, the more dips and peaks. So I would say they are also a little closer than for a smaller n.
Thank you so much, Roberto.
Thank you. Thank you.
Any more questions, Alfonso, Bastian?
Fine.
So thank you so much, Roberto, for the very great talk, excellent talk. Thanks a lot, Roberto. Very
Thank
nice
you.
topic,
Thank
very
you,
nice talk.
Antonio. It was my pleasure to see you, even though from far away.
We usually had a biannual conference, and in January, the week of the 8th of January, we will have a conference of high energy physics. Will be nice. It will be great if you can come. We had every 2 years.
Every 2 years. Okay, so let me know when it's gonna happen. This January I am already traveling, and there is the GGI school, but maybe the next one.
It will be in Valparaiso, the conference,
Mhm.
at the Technical University Federico Santa Maria. But we had it every 2 years, so the next edition will be 2027, second week of January.
Okay, all right. Yeah, the 25 is definitely not possible, but I'll keep in mind for 27.
Thank you, Roberto. Thanks a
Thank
lot for
you.
the very nice talk.
My pleasure.
Have a
Okay.
nice time.
Thank you, guys.
Enjoy lunch if it's the correct time now.
Yeah. Thank you.
Bye.
Thanks a lot. Bye.
Bye-bye.
Bye. Bye.